Let's continue with our discussion on axiomatics and proofs. In this video, we're going to be talking more about the proof side of things. So let's start with a very basic form of proof. So here's what it looks like. So one basic proof form is the following. So first thing is you already know, for example, all A is B. And then the second statement that you would say is that, well, X is A. And then you could conclude from your first line and your second line that therefore X is B. Let me just mention real quick these dots right here in this triangle formation. This should be read as the word therefore. Okay, so whenever you see dot, dot, dot like that, that just means therefore. The book uses this notation a lot, so I figured I would clarify this for you. So anyway, this is the basic proof form. We're trying to conclude that X is B, and then the way that we do that is we know the fact that all A is B, and then we say, well, X is A, and then conclude X is therefore B. So a geometry example of this is the following. So the statement that we know already is that all equilateral triangles are isosceles triangles. Okay. The second statement is that triangle ABC is an equilateral triangle. And then our conclusion, statement 3, is therefore triangle ABC is also isosceles. All right. So this could be summed up. This whole thing can be summed up with the statement. Well, maybe I should actually say that this first line right here can be summed up with the statement. If this, well, I'll just say A is an equilateral triangle, then A is an isosceles triangle. So this is an if-then statement. If A is equilateral, then A is isosceles. Right? So that leads into our discussion on if-then statements. So obviously, just based off of this basic proof form, if-then statements are just gonna come up a lot when it comes to proofs and just theorems and proving things and all of this stuff. So they're gonna be very important in this entire semester. So let's just talk about them now. So if-then statements. So usually there will be some context to your if-then statement. So the context up here is that we're just working in geometry. But some of the examples that you might see are like real life examples, in which case it might make more sense to have some context for the situation. And so the context that for the situation that I want to talk about in this example will be that Mary just went on a walk. She just got back, right? And then there's going to be two statements associated with this context. Statement P is that Mary brought her umbrella with her on that walk. Okay, and then statement Q is Mary came home dry. So let's interpret some statements. So here I have some notation here. So I have P and then an arrow pointing towards Q. I have a Q and an arrow pointing towards P. And then I have tilde Q pointing towards tilde P. Okay, so let's break down what this notation means. So, of course, P and Q are just the statements that we said above. What does this tilde mean right here? Well, I have it written here. Tilde is just a symbol for negation. So tilde P means the negation of the statement P. So I'll talk more about this later, but basically what this tilde does is it just takes the statement P and just makes it false. So for the statement P, tilde P, if P says Mary brought her umbrella, tilde P would be Mary did not bring her umbrella. And Q is Mary came home dry, then tilde Q would be Mary did not come home dry, Mary came home wet. So that's what this negation does. So anyway, what does P with an arrow pointing towards Q mean? So it can be read as any of P implies Q, if P, then Q, or P only if Q. Okay, so P implies Q, if P, then Q, and P happens only if Q happens. Those are three different ways of interpreting P with an arrow pointing towards Q. Usually I will read P arrow towards Q. I'll just read that as P implies Q. That's usually the way that I read the statement. P implies Q. Okay. Anyway, so let's actually interpret this. So P says that Mary brought her umbrella. Q says that Mary came home dry. So if I wanted to translate P implies Q into a sentence, I could say that Mary brought her umbrella implies that Mary came home dry. It might make a little bit more grammatical sense, or might just sound better to say, if Mary brought her umbrella, then Mary came home dry. Keep in mind that this can be interpreted as a true statement regardless of whether or not it rained out during that walk, right? So our context had nothing to do with whether or not it was raining outside. So it's just saying, well, if she did bring her umbrella, then in any situation she would have came home dry. So if she brought her umbrella, then Mary came home dry. You might want to say use P only if Q here, but it sounds a little bit weird to say that Mary brought her umbrella only if she came home dry. It just kind of sounds a little bit weird, but P only if Q does actually sound a little bit better in other situations, which maybe we'll talk about a little bit later on, but not right now. Okay, so that's P implies Q. Let's do Q implies P. So whenever you have a statement P implies Q, the statement Q implies P is called the converse of our original statement. Okay, so you can think of it as like the other direction of that statement, right? So you have P implies Q, and then if you put P and Q in the same place, but just reverse the arrow, you get that statement, which is the converse. Q implies P. Q implies P is the converse. All right, so anyway, if Q, then P. Let me bring this down a little bit. Put this right here. All right, so if Q, if Mary came home dry, then Mary, I'll put in parentheses, must have brought her umbrella. If Mary came home dry, then she must have brought her umbrella on the walk. Okay. So that's what this statement literally means. I just put the must have in parentheses just because it just sounds a little bit better in terms of the grammar. Okay. So that's what this statement literally means. If Q, then P. If Mary came home dry, then she must have brought her umbrella. So is this statement true? Is this statement logically equivalent to the statement P implies Q? Well, I would say no. So if I go back to the previous statement, if Mary brought her umbrella, then Mary came home dry. This is true regardless of whether or not it rained out, right? So this is true no matter if it rained, because if she rained, her umbrella would have kept her dry, or if it didn't rain, because obviously there would be nothing to make her wet. Whereas on the other hand, if Mary came home dry, so if we did know that it was raining out, then Mary coming home dry would tell us that she must have brought her umbrella, right? So in the context, if the context were that Mary went on a walk while it was raining, then the converse would also be true. The converse would be logically equivalent to our original statement. But we don't know whether or not it rained out. So if the context were to be clarified to say that it was not raining out, then the statement would not even be a true statement, because if Mary came home dry, then we would have no way of knowing whether or not she brought her umbrella, because, maybe she just didn't bring her umbrella, but there was no rain, so she didn't get wet. Okay, so the point of that is just to know that the converse does not also have to be true. So the converse of a statement is independent of the original statement being true. Okay, so moving on to the contrapositive. So this is the statement not Q implies not P. So we call the statement not Q implies not P the contrapositive of our original statement P implies Q. And it turns out to be logically equivalent to the original statement. So again, let me remind you, tilde P means not P, or the negation of P. Let me bring this down again. All right. So if Q is false, then P is false. That's what this statement right here says. Q is false, then P is false. So let's put that into a sentence. So Q says that Mary came home dry. If Q is false, then that means Mary came home wet. Then P is false. Then Mary did not bring her umbrella. Okay, so we negated these two statements by saying Mary came home wet instead of dry, and then Mary did not bring her umbrella instead of she did. Okay, so this conveys the same exact information as if she brought her umbrella, then she came home dry. In the two situations, if it's raining out, so if it's raining out, we'll do this case by case. If it's raining out, then if she brought her umbrella, then that would tell us that she came home dry, right? Whereas over here, if she came home wet while it was raining out, then that means that she did not bring her umbrella. So both of those are true in that situation. Whereas if it were not raining out, then Mary would never have come home wet. So the statement is true to begin with, right? So that's kind of a weird thing, which I won't talk too much about. So if P then Q, this is like a weird logical thing. I don't want to get too deep into the weeds here, but if a statement P is already false, then the statement if P then Q is automatically true. I don't think that it's worth spending too much time on this, so I'm just gonna kind of avoid that. But anyway, the upshot of all of this is that this statement right here just is conveying the same exact information as if she brought her umbrella, then she came home dry. If she came home wet, then she couldn't have brought her umbrella in the first place. You could have said either of these statements and they would have conveyed the same exact information. They're logically equivalent. All right, cool. So that's enough of me talking. I think it is worth your time for you to try an example yourself, because logic is really like something that like is not going to make a ton of sense to you unless you start toying with it yourself. So please take the time to try this example on your own. So let me tell you the context real quick. So the context here, we're in geometry. R is a rectangle. We already know that this thing R is a rectangle. And then we have two statements. We have the statement P, which is R is a square. And then the statement Q, which is that R has all equal sides. So interpret the statements P implies Q, the contrapositive, not Q implies not P, and the statement Q implies P, which is the converse. And when you do this, I want you to think about whether or not the converse is true in this situation. So please pause the video, give this example a shot, and then unpause, and then see if you get the same things as me. All right, give you a couple more seconds to pause, and then we will go over. All right, so I'm going to assume that you've had enough time to try this problem. So anyway, let's give it a shot together. All right, so context, R is a rectangle, P says R is a square, Q says R has all equal sides. Let's interpret P implies Q first. Okay, so P implies Q tells us that if R is a square, then R has all equal sides. Okay, so that's one interpretation. Let's think. Does P only if Q sound grammatically right if I do this? So, so R is a square only if R has all equal sides. So this is a case where P only if Q actually sounds right in the given context. So this is an example of how P only if Q actually sounds right if I put it into sentence form here. So R is a square only if it has all equal sides. Rectangles are squares only if their sides are all equal. Okay. So that's all well and good. Let's do the contrapositive next. Well, maybe before I go there, let's just keep in mind this is a true statement, right? So R is a square tells us that the sides all have to be equal. That's just definition of square. Anyway, contrapositive next. So not Q implies not P. So Q was R has all equal sides. So not Q says R does not have equal sides. So that's not Q. And we'll say if R does not have equal sides, then R is not a square. Okay. If R does not have equal sides, then it can't be a square. So that conveys the same information as R is a square only if it has all equal sides. So rectangles are squares only if they have equal sides. So you could restate that as if it doesn't have equal sides, then it's not a square to begin with. Okay. let's do the converse now, which doesn't always have to be true, and then we can examine whether or not that's actually true in this case. So converse will be Q implies P. So the converse says, so Q says R has all equal sides, P says R is a square. So if R has all equal sides, then R is a square. So is this true? So to determine whether or not this is true, I have to go back up to the context, right? So the context was that R is a rectangle. So the context actually changes things in this case. So if R is a rectangle, then that tells us that the angles are all 90 degrees, right? So if I have the angles are all 90 degrees, and then additionally I have that all of the side lengths are equal, then yes, I can conclude that R is a square. However, if I did not know that that R was a rectangle to begin with in our context, then R could be anything. So it could be a rhombus in this case. So in a rhombus, you can have all equal side lengths, but the angles are not 90 degrees, and so it would not be a square. So a rhombus has all equal sides, but it is not a square. But in this case, we are assuming from the start that R has to be a rectangle. And so Q implies P, the converse, because of our context, because of our prior assumptions, Q implies P is actually a true statement. So we'll put a little check mark there because it's true. Okay. So normally this converse would not be necessarily true. So the converse here is not always going to be true, but it is true if we assume that we're starting with a rectangle. Okay. So anyway, we now have that P implies Q is true, and Q implies P is true. Q implies P, I could just write this backwards as like P on the left, Q on the right, and the arrow points from Q to P. Same as it over here, I just did it backwards. So I have P with a right arrow to Q, and then P with a left arrow, and then Q. And commonly, we will just, instead of writing P right arrow Q and then P left arrow Q, what we will often do is P double arrow Q to indicate that both directions of this implication are true. Furthermore, so if P, then Q can be restated as P happens only if Q happens. And if Q, then P can be restated as P happens if Q happens. All right, the right thing happens if the left thing happens. P happens if Q happens. Okay, so I have P happens only if Q happens, and P happens if Q happens. So P if and only if. I should have had an if right here. There we go. Now that's correct. So P happens if Q happens, and P happens only if Q happens. So this will often be stated as P if and only if Q. So P double arrow Q can be read as P if and only if Q, And we often abbreviate this to PIFFQ. So PIFFQ, usually you will read it as P if and only if Q. All right, and so that's the problem. Thank you for listening.